Standing waves are very important because most musical instruments that I can think of will operate because they set up a standing wave, whether in air, if it's a wind instrument, or by strings, if it's something like a guitar or a bass or a violin. And the IB also thinks standing waves are important, and so we are going to learn about them. Get ready! Since we can't see standing waves in air very much with sound waves, we tend to usually try to visualize them with transverse waves. Hopefully your teacher has given you something like a slinky and allowed you to set up standing waves, because that is kind of fun on a slinky. And some key things about the standing wave, once you get it, is that there'll be certain points that are frozen. And those have specialized name of nodes. And that's what you're seeing at these points here. And you can think that node is a way of saying no motion, because those points will not be moving. The opposite of those, the parts that are moving like crazy, up and down repeatedly, these are your antinodes. And as you can guess, that means the opposite of a node. Now, the key thing with standing waves is the energy is not moving along through it. Instead, we can say that it's stored on the medium, and the medium's just oscillating back and forth. You have no traveling or transmittal of energy. It's kind of cool how standing waves actually get formed. Let's say that you've got a really long string that just goes on and on forever and ever. If you send a pulse along here, you can send as many pulses as you want. If it's an infinitely long rope, you'll never get any standing waves because you have to have a spot where they get reflective. So let's say that this is a wall right here. The fact of the matter is that you have to memorize is that standing wave has to have one end fixed on the medium. The string or the slinky has to have an area where reflections can occur for this to be set up on a string. And these reflections have to occur because as this wave is going to go down, it's going to hit the wall, and it's then going to reflect on the other side and start coming back. Now, if you start sending more waves, they're all going to be trucking down along this wave, and then they're all going to hit the wall, and they're all going to start coming back. And then you have a whole collision of waves. But fortunately, the waves do some clever things, and they will both constructively and destructively interfere with each other. So let me drag on some important points. That they are continually going to be interfering, the ones going this way, and the ones coming back, in a couple different ways. If they're destructively interfering, troughs and crests, then you'll get a cancellation, and you'll get a node, the spot where there's no motion. If you have crests and crests, or troughs and troughs, they will sometimes make a super crest, sometimes a super trough, and you'll get an antinode where you get maximum amplitudes. When you pluck a guitar string, ding, you may not have known it, but you are setting up standing waves on that string, and more than just one type of standing wave. The simplest wave that you're standing up is where the two ends of the guitar string are acting as your nodes because they're fastened to the body of the guitar and not allowed to move. So there you have your no motion. And then right in the middle is your antinode because you have the maximum motion. And let's say that L is the length of the string. Now, if this were a whole full-on wave, then it would continue for one wavelength over to here. And that would be your whole wavelength. But we don't have that long, but we can say that one wavelength would actually be twice as long as the length of your strings. So that's how we get this equation. Then this is your old, boring, simple wave equation. Velocity equals f lambda. But you can plug in for the lambda as 2L, and you end up with this one. And then this is just a rearrangement. These are some helpful wave equations that you don't have to memorize, but you should be able to rationalize where those come from. Here's something that maybe string players know, but I didn't know this until a while ago, and I thought it was pretty cool when I learned it. And that is that you can easily set up a higher frequency or a second harmonic also on a guitar string. If you assume that the middle point of the string will be a node, you can lightly place your finger there. Then about a quarter of the way along the string, bling, you can pluck that, and the middle part will stay motionless, and then the other parts start vibrating at a higher frequency than what you did to get that fundamental frequency, or first harmonic. And you're setting up a wave like this, where the middle is not moving, and in this case, the length of the string is a full wavelength. And then these other equations do fall out of that. You can even take it another step, and you can set up a node at the 1/3 spot and the 2/3 spot, and cling, and then set up an even higher frequency on your guitar string or violin string or bass string as well. The general equation that you don't have to memorize, but that does come out of this, is that for standing waves on strings, the wavelength will be 2L over N, where N is going to be 1, 2, 3, 4, etc., based on the fundamental frequency, or which harmonic you're using. If you're using the first harmonic, you plug in 1. If you're using the second harmonic, plug in 2, etc., etc. With string waves, keep in mind that the second harmonic is twice the frequency of the fundamental. The third harmonic is simply 3 times the frequency of the fundamental. With air instruments, using longitudinal waves, things can get a little more complex. Let's start with a type of instrument that is what we call closed, meaning one end of the tube is closed and the other end is open. This might be like a clarinet or a saxophone, where here is the mouthpiece on this end, which is going to act like a node because your mouth is clamped down on it, and air, while there is air moving, it can't move freely. This part, the antinode, is the bell, where you have the most motion. And here, often, longitudinal waves are sort of represented as string waves because people are better at picturing string waves, where here's the node, molecules can't move. Here's the antinode, where the string's moving at maximum amplitude, or the air molecules are moving at maximum amplitude. Now keep in mind, this is the simplest way, or the fundamental frequency for a closed tube. And so if the length of the tube is L, this is only 1/4 of a wavelength, as we've said here. Or you can reverse that and say that the wavelength is 4 times the tube length. And then these equations tend to fall out of that. Now for the second harmonic, at the mouthpiece you always have to have a node, and at the bell you always have to have an antinode. The next simplest thing for the second harmonic is to have one node here at 2/3 of the way, and you end up with this. Now in this case, the wavelength is going to be, the wavelength will be 4/3 the length of the tube, or you can start by saying that this length is 3/4 of a wavelength, and then rearrange it. Now notice that the fundamental frequency, second harmonic has a frequency that's 3 times, actually, the fundamental. And as we get over here to the third harmonic, now the tube has 5/4 of a wavelength on it, and you can rearrange for this lambda. But now the frequency of the third harmonic is 5 times the frequency of the fundamental. So this is a little bit more complex than the string waves. And the equation that relates the wavelengths is 4 times the length of the tube divided by n, where now n is not just 1, 2, 3, 4, 5. You have to go 1, 3, 5, etc. For waves that are open on both ends, we say that's an open tube. And so, they are open at both ends. Ignore what that said there. And for example, a flute would be that, because the flute's open on the final end, and where the player puts their mouth, that's an open hole as well. So air is able to move at an antinode on both ends. So that's why this drawing shows antinode on both ends of the tube. And for the fundamental frequency, simplest thing is to have one node right in the middle. And if we do that, the tube is, or the wavelength is going to be twice the length of the tube, because you would say that the length of the tube is half a wavelength. Now the next most complex thing, for the second harmonic, you still have to have antinodes on both ends of the tube. But now maybe we've got two nodes in the middle. In this case, and you can see it better as represented by string waves, the length is exactly one wavelength. The length of the tube is one wavelength. And so these equations then fall out of it. But the final thing worth knowing is that the second harmonic is twice the frequency of the first harmonic. So this is easier than closed tubes, I think. And then third harmonic, here you can see the tube is 3/2 of a wavelength. You eventually end up with the fact that the frequency of this one is 3 times the frequency of the fundamental. And the equation relating the wavelength to the length of the tube is 2L over n, where n is simply just 1, 2, 3, etc.